Welcome to the Deep Dive. This is where we take your curiosity, dig into some fascinating sources you send us, and really distill them into knowledge you can actually use. Today we're plunging into a world where light reveals secrets, but maybe not how you'd expect, even when it can't pass through an object. So imagine trying to analyze something like, I don't know, a thick wall or a really murky river, maybe even the dusty surface of Mars. You can't see through it, right?
Yeah.
But you can learn a ton by understanding how light bounces off it. That's basically the magic of diffuse reflectance spectroscopy, DRS for short. You've given us some incredible material on this, and our mission for this deep dive is simple: get you totally up to speed, really well informed on this powerful, versatile technique.
It's true. A lot of the, let's say, traditional analytical methods, they just hit a wall, a literal wall sometimes, with opaque samples or things that scatter light like crazy. Think about trying to use a standard microscope on, I don't know, a piece of chalk or a rock. The light just doesn't go through. And what's really groundbreaking about DRS, and we'll definitely unpack this, is that it becomes the essential tool, the indispensable tool in exactly those situations. It gives us crucial insights into what something's made of, its properties, places where other techniques are just completely blind.
Okay.
So, yeah, our exploration today will guide you through the basic principles that make it work, the clever instruments they use, the absolutely critical step of calibration, can't skip that, and then we'll sort of journey through the applications, which are surprisingly diverse. I mean, it touches everything from the food you eat to priceless art, even exploring other planets.
That really sets the stage perfectly, because the very first thing I think we need to get our heads around is this fundamental shift,
Right.
this change in perspective. Normally, when people think spectroscopy, they picture light going through something, transmission.
Right.
You're trying to beam through, say, a colored liquid and see what gets absorbed.
Standard stuff.
But with diffuse reflectance spectroscopy, DRS, we flip that completely.
Sure.
We're measuring the light that reflects from the surface after it's actually gone in a little bit, scattered around inside the material, and then come back out. So instead of trying to shine light through that solid brick wall, which is pointless, we're carefully analyzing the light bouncing back at us from its surface. That bounce is the key. And it gives DRS this unique edge, really unparalleled, making it vital for samples that are just too thick or too cloudy, too opaque for the usual methods.
Exactly. And to really get that bounce, it helps to break down reflection into two main types. First, you've got specular reflection. Think of a mirror.
Okay.
Light hits a smooth surface, bounces off at an equal but opposite angle, like seeing yourself in glass. In DRS, actually, we often try to minimize that specular part. It doesn't tell us much about what's inside the material, just the surface smoothness.
Okay.
What we really want to capture, to maximize, is diffuse reflection. This happens when the light hits a rougher surface, penetrates just a bit, scatters around inside like a pinball machine, and then emerges again, but in all sorts of random directions.
Like it gets lost for a second.
Kind of, yeah, like light getting lost in a little maze within the sample and then finding its way out again. So for materials like powders or rough solids, optimizing the measurement setup to grab as much of that scattered light is really crucial. And it's this internal scattering and absorption process that creates a unique spectral signature, basically a chemical fingerprint. Every material interacts with light differently across the spectrum, absorbing some wavelengths, reflecting others, and that fingerprint, that's what lets us identify stuff.
Okay, so we get this fingerprint from the reflected light. That's amazing. But usually, in science, just knowing what's there isn't always enough. You often need to know how much. So how do we take these diffuse reflection measurements, which sound inherently messy, right, with all that scattering, and turn them into something, well, quantitative numbers? This is where it gets really interesting, I think, and where this thing called Kubelka-Monk theory comes in. Sounds important.
Oh, it's absolutely the cornerstone for quantitative analysis in DRS. And, what's crucial to grasp is the problem it solves. If you have a clear liquid, you use Beer-Lambert law. Simple relationship. More stuff means more light absorbed. Easy.
Oh, I learned that in chem class.
Exactly. But in an opaque scattering sample, light isn't just absorbed, it's bouncing all over the place. It's almost impossible to isolate just the absorption. Kubelka-Monk theory, which actually goes back almost a century, offers this really elegant solution. It creates a mathematical link between what you measure, the diffuse reflectance, let's call it R, and the material's own optical properties. Specifically, its absorption coefficient, how much light it absorbs, we call that K, and its scattering coefficient, how much it scatters light, we call that S.
Okay, CAN-S, absorption and scattering.
Right. And the theory gives us this thing called the remission function. It looks like FR equals 1 minus R squared divided by 2R. Now, the genius part is this. For an ideal sample thick, scatters light well, absorb or spread out evenly, this FR value turns out to be directly proportional to the ratio K divided by S.
K over S, okay.
Even better, in many real-world cases, especially if the scattering S doesn't change much, FR ends up being directly proportional to K, just the absorption. And K, the absorption, is directly proportional to the concentration of whatever is doing the absorbing.
So you get back to concentration.
Get back to concentration. It's like, imagine trying to read a message on crumpled, maybe slightly see-through paper. Kubalka Monk is like having a magic way to mathematically flatten it out so you can read the message clearly. This transformation lets scientists effectively simulate an absorption spectrum just from the messy reflectance data. It makes precise quantitative measurements possible even in these really complex, opaque samples. It really unlocks the quantitative power of DRS. It's not just what, but how much.
That's a fantastic explanation. Taking that chaotic, scattered light and, like you said, flattening it out into a clear number, that's powerful.
Yeah.
Okay, so we get the why now. Let's switch gears to the how. How do you actually do this? What does the equipment look like? What's the setup?
Good question. So a typical DRS setup has a few key parts working together. You need a light source, obviously. Often it's a tungsten halogen lamp, good for visible and near-infrared light. Or, if you need UV light too, a deuterium tungsten halogen lamp.
Okay, light source, check.
Then you need a way to get that light onto your sample and, crucially, collect the light that bounces off. That's usually done with a reflectance probe. Often these use fiber optics, which are really efficient for guiding light.
Fiber optics, right.
And finally, that collected light has to go somewhere to be analyzed. It goes into a spectrometer. Many modern ones use what are called dispersive gratings. These are like super fine prisms or ruled mirrors that split the incoming light into all its different colors, its wavelengths. The neat thing is they often allow simultaneous detection of all wavelengths at once. No moving parts, which makes them fast and pretty robust.
Ah, so it sees the whole rainbow at once, basically.
Sort of, yeah, the whole relevant spectrum. And one really critical component for collecting that diffuse light effectively is often an integrating sphere. Picture a hollow ball coated on the inside with a material that's super reflective but also scatters light really well, like a matte white paint. This sphere ensures that almost all the light bouncing off the sample, no matter what weird direction it goes in, gets captured and eventually funneled to the detector. It sort of homogenizes the reflected light.
An integrating sphere. Okay, that makes sense for catching all that scattered light. Now, you mentioned calibration earlier. You said it was critical, and I know with any precise measurement, calibration is key. But how does it work specifically here? How do you calibrate for diffuse reflection?
Yeah, non-negotiable is the word. Absolutely essential, because DRS measurements are always relative. You're not getting some absolute reflectance value out of thin air. You're always comparing your unknown sample to a known standard. Conceptually, the ultimate reference, the primary standard, is this theoretical idea: a perfect reflecting diffuser. A mythical material that would reflect 100% of all light hitting it, perfectly diffusely, scattering it evenly in all directions. Its reflectance value would be exactly 1.0.
But that doesn't actually exist, right?
Exactly. It's an ideal. So in the real world, we use materials that get pretty close. Common standards are things like magnesium oxide, MgO, or barium sulfate, BaC4, sometimes opal glass. Pressed plaques or plates made of barium sulfate are really highly regarded. They're very matte, opaque, incredibly uniform. They make excellent transfer standards.
Transfer stamps.
Yeah, meaning you can use them to accurately transfer a calibration from, say, a master instrument to your working instrument. And, connecting this to the bigger picture.
Yeah.
Calibrating these physical standards themselves. That's serious business, often done by national standards labs like NIST in the U.S. They perform these complex absolute reflectance measurements, comparing the material standard back to that theoretical perfect diffuser. It requires specialized equipment and painstaking procedures.
Wow. But that high level of precision is what ensures that measurements made in different labs on different instruments can actually be compared reliably. It ensures consistency worldwide.
Okay, so the standards themselves are carefully calibrated. What about using them in the lab day to day? Any practical tips for getting good data?
Oh, definitely. Several key things. First, warm-up time for your light source. Always give it a good 15-20 minutes to stabilize. Its output changes as it heats up.
Good tip.
Second, dark measurements. You need to measure the signal when no light should be hitting the detector to subtract any electronic noise or stray light. Use a shutter if your system has one, or point the probe into a truly dark space like a light trap. Crucially, never just turn off the light source for your dark measurement or point it at something black. Even black objects reflect some light, and turning off the source changes its thermal state.
Mm.
You know that about black objects. Okay.
Yeah. Then, consistency in sampling geometry. Keep the angle and distance between your probe and the sample exactly the same for your reference measurement and your sample measurement. Even small changes can affect the reading.
Makes sense.
And finally, optimize your integration time. That's how long the detector collects light. Set it so your reference standard reads somewhere around 80–90% of the detector's maximum capacity. This gives you the best signal-to-noise ratio. You want a strong signal, but you don't want to saturate the detector. Modern software often helps with this and might have other corrections too, like for nonlinearity or electrical dark signals.
That's incredibly practical advice. It really shows the detail needed for reliable results. Now, think about applying this, especially in the world of color. You sometimes hear two terms, spectrophotometer and colorimeter. They sound similar, they both deal with color. Are they the same? Or what's the difference?
Yeah, that's a really common point of confusion, and the distinction is important for choosing the right tool. A spectrophotometer, which uses the DRS principles we've been talking about, performs full spectrum color measurement. It measures the light reflected or sometimes transmitted across the entire visible spectrum, wavelength by wavelength. Like we said, it gets the whole fingerprint.
A detailed picture.
Exactly. Highly precise, very detailed spectral data. This makes it incredibly versatile. It's the tool for research, for developing new colors, for really complex quality control. For instance, it's the only way to accurately measure metamerism. When two colors look the same under your store lights, but totally different outside in the sun.
Oh yeah, happens with clothes all the time.
Right. A spectrophotometer can predict that because it measures the full spectrum, not just how our eyes see it under one condition.
Okay, so that's the spectra. What about the colorimeter?
A colorimeter is generally a simpler device. It performs psychophysical sample color analysis. Big phrase, but it just means it's designed to mimic how the human eye perceives color. Instead of the whole spectrum, it usually uses filters, maybe red, green, and blue, to get broad measurements that correspond to how our eye's cone cells respond. It gives you numerical values, often called tristimulus values, like CIE lab, which represent the color as we'd perceive it.
So it's more about matching human vision.
Precisely. Colorimeters are typically more portable, often faster, usually less expensive. They're great for straightforward tasks. Like, is this batch of plastic the same color as the master standard? Pass, fail. Or checking if a dye is fading. Quick comparisons in manufacturing QC.
Right, speed and simplicity.
Yeah. So the bottom line, spectrophotometers give you ultimate detail and flexibility. Multiple light source simulations, different observer angles, geometry choices. They're for deep analysis, color formulation, and research. Colorimeters are your workhorses for quick routine color checks against a standard, correlating directly to human perception.
That really clarifies it. Different tools for different jobs, even if they both measure color. Okay, let's get to the really exciting part. Where is this amazing DRS technique actually making a difference out there? You mentioned food, art. Let's dive into those applications. Prepare for some genuine aha moments, because its ability to work non-invasively with minimal sample prep, it opens up a lot of doors.
It really does. The applications are incredibly broad. Let's start with food science and safety. DRS is absolutely vital for understanding how light affects opaque foods, photochemical degradation, the fancy term for it. Think about oils going rancid when exposed to light, or that light-struck sort of skunky flavor that can happen in beer stored in clear bottles. UV light reacts with hop compounds. Not good.
Right, I've heard of that with beer.
Traditional methods struggle because, well, beer isn't transparent, oil isn't always clear. DRS can analyze these directly. And what's really fascinating, almost futuristic, are some advanced DRS techniques, like one called diffuse reflectance laser flash photolysis, or DRLFP. This allows scientists to remotely evaluate frozen or solid foods, sometimes even through the packaging, without having to thaw them out or take a physical sample.
Wow, no way. That's huge for quality control.
Huge. Imagine checking the quality of frozen fish or meat without defrosting whole batches. Faster checks, less waste, safer food. Beyond degradation, it's widely used for food composition analysis, measuring protein or oil in soybeans, the chemical makeup of barley for brewing, and detecting contaminants or fraud. Things like mycotoxins in grain, or spotting fake olive oil bulked up with cheaper oils, or even corn syrup added to honey. DRS can pick up those subtle chemical differences.
Detecting fake olive oil and testing frozen food without touching it, that's seriously impressive. Big wins for industry and for us consumers.
Absolutely. Now, shift gears to heritage science and art conservation. Here, DRS is just invaluable. Its biggest advantage, it's non-destructive. Conservators can identify the pigments used in a centuries-old painting, analyze ancient textiles, even sometimes reveal hidden murals or preliminary sketches underneath the visible paint layers, all without taking a sample or causing any damage.
That's incredible. Preserving history without harming it.
Exactly. There was a great example where DRS helped figure out which pigments on a medieval manuscript were original and which were added in later restorations. Crucial info for deciding how to conserve it properly. It allows for measurements right there, on site in a museum, at an archaeological dig, which is often essential for fragile artifacts.
Okay, food, art.
Yep.
What about medicine?
Big impact there, too. In the pharmaceutical industry, DRS provides rapid, non-destructive analysis of compounds. Think active pharmaceutical ingredients, or APIs, the actual drug components in pills or creams. It can be used right on the production line for online process analysis and quality control. Imagine checking the exact dose in tablets as they're being made, ensuring every single one is right, without having to pull them aside and destroy them for testing. Much more efficient.
Yeah, better quality control.
Definitely. And in medical diagnostics, it's showing huge promise. Researchers are using DRS to look for biomarkers, biological signals linked to diseases like cancer. By analyzing how light scatters and is absorbed by tissue, you can potentially get information about tissue structure, blood flow, oxygenation, things that change with disease. The hope is this leads to faster, non-invasive diagnostic tools, maybe point-of-care devices that a doctor could use for quick screening, reducing diagnosis times, and maybe avoiding invasive biopsies in some cases.
So it's not just looking at paint, but potentially looking inside you non-invasively to understand health. That's quite something.
It is, and the reach continues. Environmental science and agriculture use it too. Think about monitoring plant health from afar, maybe using drones or satellites equipped with DRS sensors, identifying different types of vegetation, assessing water content in leaves, checking nutrient levels, all based on how the leaves reflect light. This helps farmers optimize irrigation, spot plant stress early, manage crops more effectively.
Smarter farming.
Yep. And in core materials science, it's fundamental for characterizing all sorts of materials. Powders, thin films, coatings, solid catalysts, understanding their optical properties, how stable they are, essential for developing new materials and products, and maybe one of the coolest applications, planetary science.
You mentioned Mars.
Exactly. DRS instruments are crucial tools on Mars rovers like Curiosity and Perseverance, and on orbiters circling other planets and moons. They analyze the light reflected from rocks, soils, even atmospheres to tell us what minerals are there, what molecules might be present. It's how we map the composition of Mars, look for signs of past water, and basically unravel the geological story of other worlds. It's our remote analytical eyes across the solar system.
Wow. Okay, what a journey we've just taken. From checking our beer to analyzing Mars rocks. So what does this all really mean for us? We've seen that diffuse reflectance spectroscopy isn't just some obscure lab technique. It's like this revolutionary way of seeing. It unlocks information from materials that used to be total black boxes, totally opaque. From making sure our food is safe and preserving priceless history, to potentially diagnosing diseases earlier and even exploring the cosmos. DRS is clearly a seriously powerful and incredibly versatile tool. It keeps pushing the boundaries of what we can know about, well, pretty much everything around us.
Yeah, and what's truly profound, I think, is how it highlights a simple idea. Sometimes just shifting your perspective, your methodology, moving from trying to look through something to looking carefully at what bounces off it, that shift can open up entirely new scientific frontiers. And that leaves us with a pretty compelling thought, doesn't it? What other opaque problems are out there in science, maybe in society too? Problems that are just waiting for someone to find a clever new way to reflect light on them, revealing solutions and insights we can't even imagine yet.